In this video, we're solving the logistic equation. Now, the logistic equation generally looks something like this, and it's a very long process to solve. Usually, step one is to verify that something like this is true. So, if it was like an exam question, you'd normally be given this as a part A. Easiest to start from the right-hand side. So 1 over P and 1 over 300 take P. You would want to be timesing or cross multiplying. So 300 take P there and P there. So what we got to do is write the first thing as 300 take P. So that's foiling the 1 in. And then write the second thing as P over P lots of 300 take P. And now that we've cross multiplied, they have the same denominator. So we've got 300 take P over P 300 take P. And what do you know? That is what we wanted. So it's a bit weird because we started from the right-hand side of the equation. But we basically went from the messier version to the cleaner version. And I guess what I should do is write what we actually started with. Okay. Now, in general, sometimes you're not given the show that. You can have this on your cheat sheet as an identity, and I would highly recommend it. But to solve this properly, we use something called partial fractions. At the end of the video, I'll show you how you could get this question without a show that, but I will get through the actual solving of the logistic equation first. So we're trying to model this bear population. They start with 64 bears, and the growth rate is that. So that's what I'm going to start with for our differential equation, and we'll see if we can solve it. Okay, so what we want to do first is we want to write to P to T. So you're going to be left with 0.13 over here, and we're going to divide out by all this. So 1 over P1 take P over 300. Next step that we got to do is we have to times the top and the bottom of this fraction by 300. So on the bottom, I'm going to still have P there, but I'm going to pull the 300 into the brackets. And you're just left with that. So I might just go times by 300 over 300 to the left-hand side. So just explaining what we're doing there. Okay, now here is where we want to use our identity. So we've just proved that that thing equals that stuff over there. So this is 1 over P plus 1 over 300 take P times the P to T should equal 0.13. So this we can just say this is from part A. Now we can integrate both sides. This is actually a separable differential equation. So 1 over P, so to P to T. T is 0.13 to T. So maybe you just get like integrate both sides. Now it's quite common you'll get this as an exam question. I'm really trying to show you the best notation here, just to like really explain what you're doing if it's like a show that question. Okay, so this just becomes sort of like the standard thing that happens with separable differential equations. You can think of it like the t's are cancelling out, even though technically that's not exactly what's happening. And 0.13 to t. So now I can just integrate both sides. So we get log of the absolute value of p. The log of the absolute value of 300 take p. You have to be really careful here because of this minus sign in front of the p. That minus sign, we essentially divide by -1, but more or less the minus sign just comes out here. And we get 0.13t plus C1. So C1 is in R, that's a constant. Okay. Now, we can use our log laws on the left-hand side to combine this into P over 300 take P. And just explaining what we've done the log laws. Okay, then what we want is we want to raise e to the power of both sides. So e to the power of 0.13t plus c1. So maybe like e to the power of both sides. Again, I'm doing the absolute most explaining you can do. You can probably get away with less, but this is an example of like everything you might want to say, especially if it was a show that or a proof or something. Okay, so we can get rid of this, so plus or minus e to the 0.13 t plus c1. I don't think that one needs an explanation. So I'm going to split, so plus or minus e to the c1 times e to the 0.13t. So this is index loss. And then we're going to rename e to the c1 as a constant. So we're going to call that constant b. Maybe b for banjo or something. 0.13t. Okay, b is plus or minus e to the c1. Okay. Now, this is a weird step. We have to flip both sides. So 300 take p on p is, let's see, I'm just going to write it like this. So I'm going to go flip both sides. Now, this is 300 over p, take p over p. And on the right-hand side, I'm going to say 1 over b is this new constant a. And we're going to write it like that. So a is 1 over b. Okay. Next, p over p is just 1. And 300 over p doesn't change. Okay, so a e to the minus 0.13t. So 300 over p is 1 plus a e to the minus 0.13t. Therefore, p over 300, believe it or not, we have to flip it again. 1 plus a e to the minus 0.13t. So this is flip both sides. And then we can just multiply by 300. Well, that was fun. All right. Now, you should probably expect this question to be in an exam. It's quite common. But that process, although it's awful, it never really changes. So put this as an example on like a cheat sheet. Next thing we have to do is find our initial conditions. So at t equals 0, p was 64. And where I'm getting that from is there are 64 bears currently. So by currently, I mean in 1998. Apologies at the start. Okay, anyway, so we got to plug in this. So we've got 64 is 300 over 1 plus a e to the minus 0.13 times 0. So 1 plus a, so you're going to get 1 plus a is 300 over 64. Therefore, a is 300 over 64, take 1, and we can work out what that is. $59 over 16. Okay, so if we put that into the equation, see what we get. So using p of 0 is 64. Initial conditions. Cool. All right. Well, that's great. Now let's graph it and have a look. Get rid of all these old graphs. Now, depending whether or not you've studied these in methods, this equation might look familiar. It's a logistic function. So what we're expecting is some exponential growth shape at the start, and then it should level off to a limiting value. Now let's fix our window. So maybe 0 to, oh, let's go for 50 years maybe. And 0 to, well, if you know about logistics, you'll know 300 is the maximum value. But let's go 400 just so we can see the whole thing. There we go. We get a lovely graph of bear population. Okay, how many bears are there in 2008? So if the start is 1998, so then 2008 would be t equals 10. So that's what we got to do here. Okay. So to get this, all we got to do is we can plug it into the equation, but what's quicker is to go trace 10. P of 10 is 149.6. So roughly 150 bears in 2008. Okay. When will the population reach 200 bears? So we can work this out. So if we want to do that, all you need to do is go into your calculator, gsolve across xcal 200 and 15.4. Yeah, we need to figure out 0 is 1998. So if we go from 1998 plus 15.4, so it's about year 2013.4. And let's convert that 0.4 into months as well to be extra fancy. So 0.4 times 12. So 4.8. And I'm going to be extra fancy. So this is 2013. The fourth month is March, April. And the 0.8, I always get this wrong. I think there's 30 days in April. So 24. If you want to be really fancy about the exact time. What's the limiting population? 300 bears. So you can read that straight off the equation. The top number is just 300 there. That's the limiting population. Or if you want, you can actually go, let's see, menu graph, draw. You can just pick a really big number, like 50 something, 298. And then if we go for our window and make it up to 200, so 200 years, and we go trace at 200, you can see that it's basically 300 there. So yeah, that's the limiting population. All right, the last thing I want to talk about is just this step here. So how do we get from this down to this? Well, usually in an exam or something, you would have a part A, just like I've done in this video, and you would have shown that already. Or the textbook is pretty keen on using this identity. But let's suppose you didn't know either of those two things. There is a very general solution called partial fractions. Now, this option is sort of the best way because it'll always work and it's a general solution and you don't have to remember a whole bunch of formulas. But technically, I don't think you need to do it in year 12. So I'd be surprised if it came up, but it can be a really useful tool for if you ever get stuck and you just can't remember what to do. This will always work and always get you out of a jam. So basically, what you want to do is write the original fraction as the two separate bits. Now, because the bottom of this fraction is already factorized, you can sort of imagine it would be two separate fractions with each of those factors on the bottom of each one. And this doesn't just work for logistic equations, this works for a lot of integrals you may need to do. But essentially, then we need to cross multiply. By the way, m and n are just numbers that I don't know yet. Based on what we've just done here, they're going to be 1 and 1 eventually, but this is how you prove that. So now we need to FOIL out. So you've got 300m take mp plus np all over p 300 take p. And so if we sort of group this up, so you've got 300m, and I'm going to go and take m lots of p. Now, really importantly, on the left-hand side, this was supposed to be 300 over p lots of 300 take p. Now, you can group out this as 300 plus 0p, right? There's no p's on the top there. So that term groups with that term, and the constant term groups with that term. So pretty much from the green equation, you're going to get 300 is 300m And for the equation that I've done in black there, I'll just color code it better. 300 is 300m. And from this other equation, we've got 0 equals n take m. So those are your two equations there, from comparing the constant term and the p term, because it's like a linear function on the top. And then from, I call this equation 2 and equation 1. From equation 2, well, from equation 1, we just get that m is 1. And from equation 2, we get that n is m, which is 1. So therefore, the original thing is 1 over p and 1 over 300 take p. That's how you prove this thing if you ever get stuck. Like maybe you forgot to put it on your formula sheet or something. You just use partial fractions.